Hello dear students, welcome to the Quantum Guru. Let's see this question of Irodov from electrodynamics, the question number 3.26. The question states, a system consists of a ball of radius r carrying a spherically symmetric charge and the surrounding space filled with a charge of volume density rho is equal to alpha by r, where alpha is a constant, r is the distance of the center of the ball. When the ball's charge at which the magnitude of the electric field strength vector is independent of r outside the ball, how high is this strength? The permittivities of the ball and the surrounding space are assumed to be equal to unity. So, this is the diagram of the question. So, there is a ball whose radius is given to be capital R, and outside the ball, in the surrounding space, there is a volume charge density. There is charge distributed there. Everywhere there is charge. So I've shown charge only up to distance, say capital R. I've shown charge up to distance capital R. The R is taken from the center of the sphere. And here the volume charge density is given to be alpha rho is equal to alpha by R. Alpha is a constant. So what we have to find? We have to find what is the charge on the sphere, this sphere. Q, such that in the outside region, outside the ball, the electric field becomes independent of R. I mean, it becomes basically constant. So let's try to find Q. So what I want to do, I want to calculate electric field at a distance R, the small r, which is outside. So electric field at a distance r, which is greater than or equal to capital R. So this charge distribution is spherically charge distribution. So we can think of whole distribution up to here. And there are charges outside here also. I can think of this whole distribution made of the so many spherical shells. So all those shells which are within small r, for that this point, say, let me say this point is say P. So for all those shells which are within the within P, so point P will be considered at exterior point. And for all those points which are outside R, here also we can think of made of so many shells. Here also I can think system to be made of so many shells like this, and here like this. So this is interior for this kind of shell, and this is exterior for this kind of shell. We know that for a uniformly charged shell, the electric field inside it is 0. If I take shell whose thickness is very small, so charge density would be constant there. So for all those points outside P, for all the charges outside P, the electric field at P will be 0. And for all charges within P, the electric field can be simply, to find electric field, what we do, we put the whole charge at the center and then we just apply the formula of the electric field of a point charge. So suppose if the charge here in the outside region up to from capital R to small r up to here, the total charge is small q, then the total electric field at this point will be simply K into total charge up to point P divided by R square. So that will be simply capital Q plus small q by R square. So we have to basically find the small q. So to find that, what I will do, I will take a shell whose radius is x and thickness is dx, something like this. So let me make this kind of a shell, and this thickness is dx. So what is the volume of the shell? Volume of the shell will be simply 4 pi x square dx. So charge contained in the shell would be the volume charge density multiplied by the volume, that is a 4 pi x square dx. And what is the volume charge density? Volume charge density at a distance small r from center is rho by r. So volume charge density at a distance x from the center is the alpha by x. So that is a alpha by x, and there that is a 4 pi x square and dx. And we have to find charge up to in this region, this gray color region. The limit of x in this gray color region will go from capital R to small r, like this. This whole thing is a small r, and this is a capital R. So total charge enclosed within that region q is the integration of dq, and here I can take 4 pi alpha outside, and within integration I have only x, and there is this dx, and integration has to be carried from capital R to small r. So that is a 4 pi alpha, and this integration will give me r square minus capital R square divided by 2, and that 2 will make this also 2. So what I have to do, I have to just put this small q from here to here. So I put that capital Q, K, capital Q. In place of small q, I am writing 2 pi alpha small r square minus capital R square, and divide by capital small r square. Some rearrangement, that is a K, capital Q, and then there will be a minus 2 pi alpha r square divided by small r square. This term will be 2 pi alpha r square by r square, that will be only 2 pi alpha plus 2 pi alpha. So how I can get rid of small r? I can get rid of small r in this expression only if this becomes 0. So even if there is some r in the denominator, so that will be of no consequence. So this whole expression will become independent of r. Independent of r only if this whole thing becomes 0. So if this thing becomes 0, mean capital Q will become 2 pi alpha r square. And this is the answer to the first part. What is the ball charge at which the magnitude of the electric field strength vector is independent of r? So that is one thing. And when that happens, what is the strength of the electric field? And then the strength of the electric field simply becomes this E becomes then K into 2 pi alpha. K is the 1 upon 4 pi alpha, 4 pi epsilon naught. This is 2 pi alpha. So then E will become alpha divided by 2 epsilon, and that is the expression. Finally, thank you.